Hey, this is Brock Lemires, and in this video I'm going to go over lab 8.2 on arrays and calculating capacitor current. All right, so the objective of this lab is just more experience using arrays, and we're going to really get into time series and manipulations that you can do on them. What you're going to be able to do on this is afterwards you're going to fill up a sine wave or create an array and populate it with a sine wave value, and then you're actually going to go through it and find the rate of change of that sine wave voltage time series and store it in a separate array, and then you'll use that to calculate the current, the electrical current through a device known as a capacitor. Your deliverables, you'll have 2 test cases that you'll screenshot and then upload your program file. All right, so here's the deal. You don't know what a capacitor is, I'm guessing. I don't know why you should. But here is what it is roughly. It is an electrical component that is found in almost all circuits, and it is a component that can store electrical energy in the form of an electric field, or another way of saying it, it can store voltage, okay? It does this by accumulating charge in a dielectric material within the device. And it accumulates the charge only when it's being charged by a source. So imagine you have a capacitor and you hook it to a battery, it'll accumulate charge, or you hook it to the wall outlet, it accumulates charge. And then what's cool about it is that when you remove the voltage source that's charging it, the charge that sits within the capacitor can actually move back into the circuit and be used by other components. So imagine that you had like a little light bulb being, driven with a capacitor, and you charge the capacitor up with a battery, you disconnect the battery, and the light bulb will actually stay on for a little bit and then it'll slowly go out. So it doesn't like instantaneously turn off. However, a capacitor is not a battery. It's a passive device. It does not generate new charge for use in the circuit like a battery or a power supply does. It only has the capacity to store existing charge that was put into the circuit. And that's where the name comes from. It's got a capacity to store charge. So if you look at the symbol for a capacitor, it looks like this. It looks like 2 little terminals, and it has 2 plates separated by a dielectric, and it has, we call it C, we give it the letter C for capacitance, and it actually has a unit of capacitance called farads, and farads was a person, and so we can say this thing has, 0.1 farads or 0.00 farads or microfarads, millifarads, etc. And the farads basically represents how much charge it will store when you put a voltage across it. Now, for this lab, here's what is interesting. The equation between the current and the voltage is not straightforward like it is for, let's say, a resistor. A resistor was governed by Ohm's law. V equals IR. A capacitor, its governing equation is the current is equal to the capacitance times the rate of change of voltage across it. So this is where you start seeing the need for what we call calculus. This is called a differential equation. It doesn't depend on the value of the voltage. It depends on how fast the voltage is changing. And we have a whole class on this, differential equation. This is a 4-credit class that you're going to learn all about this stuff. And so you might be wondering, well, how in the world am I supposed to solve something like this? This is where the power of a discrete time series comes in, because you can simply calculate the rate of change by looking at the difference between 2 points within a sine wave stimulus. Okay, so here's what we're going to be doing. We are going to drive a capacitor, or we're going to calculate for this circuit if you drive a sine wave across it. And this sine wave, we'll build a time series that is one axis is going to be time from 0 to 2 pi, and the other one is going to be the evaluation of all the time points using the sine function out of the math library. And then you will go in and you will calculate an array that holds the rate of change across this entire sine wave. Now, you may remember this because we did this in one of our prior lectures, where if you look at this, here is this little fella where we had a time series of a sine wave, exactly what you're going to do, and you find the derivative, or we don't even call it a derivative at this point. It's basically just rate of change. And you look at the difference in V, that's going to be your delta V, versus or divided by delta t. So that is the slope of the line, and that's what we call the rate of change of the line. And you do that at every point across here. And this is the equation for it. You simply use a for loop and you go through and you create an array to hold this dv dt, and you're basically going to go, okay, for this point, I'm going to look ahead, grab what the voltage is at this point, minus the voltage at this point, and that gives me the delta v, and then delta t, you already have it because it's the t step that you use to fill up your time array. So it's actually awesome. We don't even need to have calculus yet, and we can get dv dt across a sine wave, and we can use it to plug into here. You simply multiply by the capacitance of the capacitor, and you get the current. So here's how you're going to do this. You're going to create your folders on Windows for today. You're going to log in, create your folders for the lab on the Linux server, create this thing. Your source code is going to be called ICAP. And what you're going to do is you're going to set up some pound-defined macros to set the minimum and maximum time for one cycle of a sine wave, which is 0 to 6.28. You'll start with an endpoints of 10, and then you're going to set up all these variables. You'll set up an array for time, voltage, dv/dt, and the capacitance, the current of the capacitance. And then what you'll do is you'll set up a t-step variable where you'll actually calculate the time step that'll be in the array based on the number of points. You'll create a double variable to hold the capacitance that will prompt the user for. Then, of course, you got to get your loop variable in there. And then what you're going to do is this. Print to the user, hey, welcome to the capacitor current calculator. Enter your capacitance in farads. And then what you'll do is you'll fill up the time array using a for loop, fill up the v sine array using a for loop in the sine function from the math.h. You'll then do the rate of change and to fill up the dv/dt array. Then you'll use that to simply multiply it by the capacitance to fill up the ICAP array, and then print the results. So here's an example of what your outputs are going to look like. So you're basically going to say, here it is, enter your capacitance, and then it will print the index of the arrays, the capacitance the user entered, the time step, the voltage of the sine wave as it goes up and then down, and then dv/dt. You'll notice it's up and then it goes negative and then it comes back, and then the current. And you'll do that over two situations or two inputs. Okay, so here, let me show you what mine looks like just so you can see what the end result is going to be, even though it is exactly what I just showed you. So I'm going to go ICAP, hey, enter your value. I'm going to go 0.1, print the results. Okay, how about 0.05? Print the results. How about 1 billion million? Pretty big numbers, doesn't really wrap well. And then if you do too small, like 0, like something like that, all the numbers tend to be 0. But anyway, you're going to test this under two cases. So you'll crank up the endpoints to 25 so you can get a nice a nice time series that's close together. Test it for capacitance of 0.1 farads and 0.05 farads. Screenshot them, save them with the right numbers, and you're done. All right, enjoy this lab.